You know, if you just look around you, chances are you're seeing concrete. It's the silent foundation of our entire modern world. I mean, from the tallest skyscrapers to the bridges that cross massive rivers, concrete is literally the bedrock of our civilization. It's so common we kind of just look right through it, but it's always there, holding everything up.
And that brings up a really big question, right? We rely on this stuff for everything, but it can have hidden weaknesses. So how in the world do we find those tiny flaws before they turn into a catastrophe? Well, it turns out it's a high-stakes investigation that's part brute force, part brilliant science. Let's start with the brute force.
So the first stage of this whole investigation is what you could call a physical interrogation. I mean, scientists literally have to torture concrete in a lab to figure out what makes it tick, and more importantly, what makes it break. They need to find its secrets.
And believe me, this is not just some simple squeeze test. We are talking about a full-on trial by fire, ice, and force. Engineers put these concrete samples through an absolute gauntlet. They crush it, they bend it, they freeze it and thaw it over and over, they cook it in massive furnaces, and they even listen for the sound of it cracking from the inside out.
Now, the main weapon in this physical arsenal is the Universal Testing Machine, or UTM. Seriously, think of it as this giant colossus built for one thing and one thing only: to crush, pull, and bend concrete with incredible force until it just fails. This is how we find out its raw, brute strength.
But, you know, being strong today isn't good enough. The real question is, how will concrete hold up in 50 years or 100? Well, to figure that out, engineers use something called an accelerated aging chamber. It's basically a time machine for materials. It can simulate decades of harsh weather, salt on the roads, all kinds of chemical attacks, and it does it all in just a few weeks.
And what about fire? This is a huge one. That's where the elevated temperature furnace comes in. It's this incredibly specialized oven that can blast concrete with temperatures soaring up to 800 degrees Celsius. Understanding how a material behaves in a fire is, as you can imagine, absolutely crucial for building safe structures.
Okay, this next technique is just so cool. It's called acoustic emission monitoring, and it's basically like giving a doctor's stethoscope to a piece of concrete. While the concrete is under stress, these super-sensitive microphones are listening for the faint, high-frequency whispers of tiny microcracks forming deep inside. This lets us hear the damage long before we could ever hope to see it.
So all that physical data we get is priceless, but it's slow and destructive. I mean, you have to break the thing to learn about it. So the next phase of the investigation is to take everything we've learned and move from the physical lab into the virtual world. It's time to build a digital twin.
And this chart shows you exactly why we need both. The lab gives you real, undeniable results. You can't argue with them. But it's slow, it costs a lot, and you destroy your sample. The simulation, on the other hand, is super fast. You can run it 1,000 times, and it's predictive. But at the end of the day, it's still just a model of reality. You really need both working together to get the full story.
Now, the magic behind these digital twins is a method called finite element analysis, or FEA for short. It's this incredible technique that lets engineers take a huge, complex structure, like a whole bridge, and digitally break it down into millions of little pieces so they can analyze how stress flows through every single one of them.
So how does this actually work? Well, think of it like building with digital Legos. First, you create this perfect 3D blueprint of your structure. Then, the software slices that blueprint up into millions of tiny little pieces, or elements. Next, you hit it with virtual forces, the weight of traffic, the push of the wind, even the shock of an earthquake. The computer then calculates the stress on every single one of those little bricks. And just like that, you can see exactly where the weak spots are, before a single drop of concrete has even been mixed.
Okay, so this is where it all comes together. We've got mountains of data from the physical lab. We've got millions of data points from our digital twin. The final step? We feed all of that information into machine learning algorithms. We let the AI connect all the clues and, hopefully, help us design something even better. Super concrete. And just to give you a sense of the sheer scale we're talking about here, look at this number. 276. That's the number of unique, real-world physical experiments that researchers had to compile just to train a single AI model to predict how one type of concrete beam will fail. That is an incredible amount of data, and it's what it takes to teach an AI to think like a structural engineer.
So is all that work worth it? Oh, absolutely. This chart says it all. Traditional engineering models, they're pretty good, maybe 75% accurate at predicting failure. But when you feed all that data into an AI, the machine learning models can boost that accuracy all the way up to 93%. And in structural engineering, that leap isn't just a number.
It's the difference between safety and uncertainty. It could be the difference between a routine fix and a disaster. But here's the real game changer. The AI isn't just watching and predicting when something might break. It's actually becoming a partner in inventing. By sifting through thousands of variables, what kind of sand to use, what chemicals to add, it can help engineers discover brand new recipes for concrete that's stronger, lasts longer, and is way more resilient than anything we've had before.
So, after all this physical torture, all this digital modeling, all this AI, we get to the final verdict. Why does any of this really matter to you and me in our everyday lives? It really all comes down to this one powerful idea. All of this work, the crushing, the burning, the coating, it's not about a fascination with destruction. The real goal is to learn from every single crack, every failure, so that we can learn how to build the things of tomorrow in a way that they simply never break. And that just leaves us with one final, incredible thought. For the first time in history, we can stress test our most fundamental building material, not just with physical force, but with the predictive power of artificial intelligence. So what does that mean for the future? What kind of amazing, unimaginable structures are we going to be able to build tomorrow, knowing they're safer and stronger than ever before?